So let's look at an example of using direct comparison. So we have an integral here from 5 to infinity of 1 over x to the 4th plus 1. And it's not clear how you would find an antiderivative there. It doesn't seem to fit any of our tests. It may not have an antiderivative, but it's very, very close to being just 1 over x to the 4th, right? Especially as x gets very, very large, that 1 is making very little difference, right? A billion to the 4th power plus 1 versus a billion to the 4th power is a negligible difference. So when we're looking at this, the first thing we have to decide is what we're going to compare with, and it should be something very similar, obvious comparison. And also, we want to compare with those things of the form 1 over x to the p, because we know whether those converge or diverge. So, and 1 over x to the 4th is one of those. So the first step is I want you to state that the conditions are met. So remember, for direct comparison test, both those functions need to be continuous on the interval we're looking at. So 1 over x to the 4th plus 1 and 1 over x to the 4th, both those functions are continuous on this interval from 5 to infinity. So there's no problem there. And then I want to show the inequality, and the inequality should be obvious. What I mean by that is this thing shouldn't be drastically different from 1 over x to the 4th to the point where we're not sure if it's bigger or smaller. If it is too much different, then we probably need to try something else, which we'll look at in a little bit, and that's what's called limit comparison test. So adding that 1 on the bottom makes the denominator just a little bit bigger, which makes that fraction a little bit smaller. So the inequality is that 1 over x to the 4th plus 1 is, the theorem requires it to be greater than or equal to 0, which it is. And it needs to be less than or equal to the one we're going to compare with, which is 1 over x to the 4th, which it is, as long as we're on that interval from 5 to infinity again. OK. So now here's how we'll make the argument. We want to argue that the integral from 5 to infinity of this function converges. This one's smaller, so it converges. That's number 1 there in DCT. And this is why we looked at these already. This is that reciprocal power function. So since the integral from 5 to infinity of 1 over x to the 4th dx converges, and I need to see that you understand why we know that converges, and it's based off of that exponent. So I want you to say p is 4, which is bigger than 1, because that's the criteria, right? Remember from that fact before, the exponent bigger than 1, the integral converges. And so now what do we have? We have all the pieces of DCT. We have these two continuous functions. We have this inequality. The larger function as an integral converges, so then the smaller one must converge as well. So the integral from 5 to infinity of 1 over x to the 4th plus 1 dx converges by, and I want you to always say what theorem you're using, and you can just say DCT for short, by direct comparison test. So all these elements need to be in your argument. I need to see you state that these guys are continuous. You don't need to prove anything there. Just convince yourself of that. Think about the sorts of things that make functions not continuous are division by 0, negatives under a radical, something like that. Well, this thing never divides by 0, right? X to the 4th is positive, plus 1 is, or x to the 4th is non-negative, plus 1 is positive. X to the 4th could be 0 when x is 0, but we're starting at 5, so we're past any problems. So just make sure you convince yourself that you're dealing with continuous functions, and then this should be an obvious inequality. Then state why we know that that integral is convergent, and then make your conclusion that the one that we're trying to figure out is convergent by DCT. Next, we'll look at another example using DCT, this time arguing that the integral is divergent.